Welcome! This presentation brings together two complementary results on aerodynamic co-contraction in redundant aerial actuation. The common geometric object is a task fiber, a family of internal actuation states that all realize the same task. Moving within that family can change active aerodynamic promptness, passive aerodynamic damping, and power consumption. The QR code links to my website and related material. The first paper develops task fiber geometry, active promptness, and its trade-off with power consumption. It received the IQAS Best Conference Paper Award. The second paper identifies and studies the variable aerodynamic damping as a passive effect of the same co-contraction mechanism. The DOI links identify the archival publication, and the QR codes open the freely accessible preprints. The presentation combines both papers into one narrative. The starting question is what actuation redundancy provides beyond robustness and energy-efficient allocation. The key answer is that the same task can be realized by different internal actuation states. These states are task equivalent, but they need not have the same local behavior. The rest of the presentation develops this idea quantitatively. Here, the task is generated rigid body wrench. Full actuation and redundant actuation describe different properties. A fully actuated aerial system can generate arbitrary wrench in the 6-dimensional rigid body wrench space. An underactuated system has a structurally lower dimensional wrench task, commonly 4 dimensions. Total thrust and 3 torques. Redundancy instead compares the number of independent actuator variables with the dimension of the selected task. Thus, more than 4 independently commanded propellers can make a vehicle redundant relatively to that 4-dimensional task, while the vehicle remains underactuated relatively to the full 6-dimensional wrench. This distinction leads naturally to task fibers. Let V denote the internal actuation state space and W the task space. The map F assigns a task value to each internal state. For a prescribed task W, the inverse image shown in the main equation is the fiber F sub W, all the internal states V such that F of V equals W. Because the actuation is redundant, this set generally has positive dimension. Motion along the fiber changes the internal state without changing the task. The picture makes that definition concrete. The internal state space has dimension 3, while the task space has dimension 2. Each colored curve is a one-dimensional fiber. Every point on the curve maps to the same task point of the corresponding color. Therefore, the task does not select a unique internal state. It selects an entire fiber. Control allocation chooses where to operate on that fiber. The two boxes separate the current task value from its local differential. On the left, every V on F sub W satisfies F of V equals W, so the current output is identical. On the right, a small internal state variation delta V produces the task variation delta W through the Jacobian J sub F at V. Because the Jacobian depends on the operating point, task equivalent states can provide different instantaneous task rate authority. This raises the first quantitative question. How should that active readiness be measured? Given a bounded actuator rate capability, we push the admissible actuator rate ball through the task differential. The image is an ellipsoid of achievable task rates. Its volume provides a scalar measure of the available active authority. The diagram expresses this push-forward construction. The differential dF maps actuator rates to task rates. Its dual maps task rate covectors back to actuator rate covectors. The inverse actuator metric then converts those covectors into actuator rates. Their composition is the task cometric D sub V. In coordinates, the same construction is d of V equal to J sub F, G inverse, J sub F transpose. The metric G encodes the normalized actuator rate capability. The actuator metric defines the unit ball delta V transpose G delta V less than or equal to 1. The Jacobian maps this ball into the illustrated task rate ellipsoid. Its cometric is d of f. At regular internal states, the Jacobian has full row rank, so d is positive definite. The square root of determinant d is the ellipsoid volume factor. This quantity is the fiber density measure used here as an active promptness. Larger rho means more generic task rate authority under the same actuator rate budget. The operational meaning is simple. In a low-density region, the same actuator rate budget produces only a small local task rate change. In a high-density region, the corresponding task rate ellipsoid is larger. Thus, selecting a high-density point on the fiber gives the system greater instantaneous authority to change the task. Before using the determinant as an objective, there is a legitimate geometric objection. The cometric d sub v maps task vectors to task vectors, so its domain and codomain are different spaces. It is not yet an endomorphism. Consequently, the determinant and ordinary eigenvalues of its coordinate matrix D are not intrinsic quantities by themselves. A further structure is needed to identify vectors and covectors on the task side. The task metric provides that missing identification. At f of v, h maps task rate vectors downward to their metric dual covectors. The cometric d sub v maps them back upwards to task rate vectors. The red arrow summarizes their composition, a sub v, equal to d sub v composed with h at f of v. This is an endomorphism of the one-task tangent space, so its determinant and spectrum are intrinsically meaningful. The remaining question is whether the computational allocation changes with the task chart or with the auxiliary task metric. Under a task coordinate change, the unweighted proxy square root of determinant d is multiplied by the absolute determinant of the chart Jacobian. The intrinsic objective adds the factor square root of determinant h. Along the fixed fiber f sub w, both factors are evaluated at the same task value w and are therefore positive constants. They change numerical values, but not the fiber-wise ordering, maximizers or minimizers. This justifies using the simpler determinant proxy for optimal allocation inside a single fiber. With the geometric construction established, we can specialize it to multirotors. For fixed-pitch propellers, force and torque are quadratic in rotor speed. Therefore, the task differential is linear in the current speed magnitudes, and active promptness depends on the selected rotor speed state. This is the operating point dependence that redundant allocation can exploit. The multirotor task map sums the sine square contribution A sub I, V sub I times absolute V sub I over all the rotors. Differentiating gives J sub F equal to 2A times diagonal matrix of speed magnitudes. Hence, the static wrench is quadratic in speed, while the local wrench state gain is linear in the current speed magnitude. Replacing rotor speeds by squared force variables would make the allocation map linear and would hide this physically relevant state dependence. On every constant wrench fiber, we now attach two observables. The power proxy P is the sum of coefficients times the cubes of the rotor speed's magnitudes. With the Euclidean actuator rate metric, promptness ρ is the determinant-based task rate volume shown on the right. Thus, one internal state V on the same wrench fiber maps to one pair, P of V and ρ of V. Allocation at fixed wrench therefore selects both energetic cost and active authority. The next issue is whether this energy promptness trade-off always has the same form. It does not. The objective functions alone are insufficient. Their behavior after restriction to the feasible fiber is decisive. The aerodynamic dipole provides the simplest system, showing two qualitatively different fiber geometries. The aerodynamic dipole consists of two parallel rotor contributions generating one scalar force task. Depending on mounting and sign convention, the two thrusts contribute cooperatively or antagonistically. At zero inflow, the task is a signed sum of the squared rotor speeds. This minimal two-input one-task map will be used repeatedly to expose the geometry and the physical effects of co-contraction. The plotted level sets are the complete constant task fibers family of this assigned quadratic map for the aerodynamic dipole. In cooperative regions, the fibers are compact elliptical arcs. In the antagonistic regions, they are hyperbolic branches. The same nonlinear map, therefore, contains two fundamentally different feasible geometries. The comparison makes the consequence explicit. A cooperative fiber is compact, so continuous objectives have bounded tuning range. An antagonistic fiber is hyperbolic. Both rotor magnitudes can grow while their signed resultant remains constant. Hardware speed limits truncate the physically feasible branch. But within those limits, co-contraction can produce large changes in internal observables without changing the task. We now focus on the positive speed antagonistic branch with prescribed positive task W bar. The constant task equation is the difference of two square rotor speeds. Setting V2 equal to S gives the exact parametrization shown. V1 is the square root of W bar over KT plus S squared. As S increases, both speeds increase and dW over ds remains 0. The parameter S, therefore, traces a task-preserving co-contraction path along the hyperbola. Substituting this parametrization into the observables gives the first main result. Power is cubic in the two speeds, while promptness is proportional to the square root of the squared sum. Both derivatives with respect to S are positive. Consequently, minimum power selects S equal to 0 at the fiber vertex, whereas maximum promptness selects the largest hardware admissible S. More active readiness is available, but it has a strict energetic price. The profiles confirm that the fiber geometry controls the trade-off. On cooperative fibers, the two objectives vary over a limited interval. On antagonistic branches, the power objective and the negative promptness objective separate strongly and monotonically. The objectives are unchanged. What changes is the geometry of the domain on which they are optimized. The same principle extends beyond the dipole. These three extra rotor allocations realize exactly the same commanded range, but correspond to low, medium, and high promptness. The rotor speed distributions, acceleration authority, and power consumption change with the allocation. This vehicle-level example shows that task-preserving promptness tuning is not restricted to the scalar toy model. We want now to highlight a strong analogy with soft robotics and biomechanics. Consider an antagonistic variable stiffness actuator. The output torque is the difference between the two tendon forces. At zero joint displacement and with quadratic hardening, this becomes the same difference of squares map as the aerodynamic dipole. The tendon states and opposed rotor speeds therefore share the same hyperbolic fiber geometry. The mechanical example, however, distinguishes between active and passive behavior. At fixed torque, the active promptness ρ measures how internal tendon state variations change torque. The passive stiffness sigma instead measures how an external joint displacement changes torque. Their formulas involve the same tendon force slopes, and strict hardening means those slopes increase with co-contraction. Therefore, one positive constant torque motion increases both active promptness and passive stiffness. The resulting correspondence is therefore only partial at this stage. The active column is complete. The mechanical system has torque promptness and the aerodynamic dipole has aerodynamic promptness. The mechanical system also has a passive joint stiffness. The lower right cell remains open. The structure itself now asks whether an aerodynamic passive counterpart exists. To complete that lower right cell, we need an external aerial variable that changes rotor thrust, just as an external joint displacement changes tendon force. The relevant variable will be the air relative velocity along the rotor axis, namely the axial inflow. At a blade element of radius var rho, the tangential speed is v times var rho. A small axial inflow tilts the relative airflow by the angle phi, approximately equal to the inflow divided by v var rho, and therefore changes the angle of attack. With a locally linear lift law, the element thrust separates into the blue zero inflow contribution, quadratic in speed, and the orange mixed contribution, linear in both speed and inflow. After integration, the model becomes ktv squared plus or minus kdv times the axial inflow. The key point is that thrust is locally linear in inflow, while the magnitude of its inflow sensitivity grows linearly with rotor speed. We now put that single rotor law back into the aerodynamic dipole. Both propellers experience the same module-level air relative velocity u. Because their axes are opposed, the corresponding signed axial inflow are u and minus u. Neglecting mutual aerodynamic interference, the dipole task is T of u1 and u minus T of v2 and minus u. Fixing the trim pair w bar and u bar defines the fiber displayed here. Along this fiber, the trim task remains fixed, but the derivative of the task with respect to inflow can vary with the internal state. This derivative defines the passive observable. For one rotor, lambda is minus the thrust derivative with respect to axial inflow. For the dipole, sigma sub a is minus the derivative of the complete task map with respect to the common air relative velocity, evaluated at the trim. The chain rule sign make the two rotor sensitives odd. The positive sigma sub a means that the small velocity perturbation generates an opposing aerodynamic task variation. Unlike promptness, this channel is driven by an environmental perturbation rather than an internal command variation. The passive input-output map can now be written directly. A small air relative velocity perturbation delta u produces the task variation delta w equal to minus sigma sub a times delta u. This force response is generated aerodynamically before feedback correction. By selecting a different internal state of the same trim fiber, allocation changes this passive map without changing the trim task. This leads us to the second main result, which follows from two local monotonicity assumptions. First, the thrust increases with rotor speed. The constant task tangency equation then implies that delta V1 and delta V2 have the same sign. The positive orientation is co-contraction. Second, the inflow sensitivity lambda increases with rotor speed. The variation of sigma sub a is therefore the sum of two positive derivative terms multiplied by positive speed variations. Hence, positive task-preserving co-contraction strictly increases incremental aerodynamic damping. The first-order inflow model makes this mechanism especially transparent. Substitution into the dipole map yields a blue trim task term, kt times the difference of squared speeds, and an orange passive term, kd times the speed sum times u. Defining sigma sub a as kd times v1 plus v2 gives the compact affine form shown below. Along a constant task fiber, co-contraction preserves the difference of squares while increasing the speed sum. This is variable aerodynamic damping actuation. The 4-cell compass is now complete. In the mechanical row, co-contraction shapes active torque promptness and passive joint stiffness. In the aerodynamic row, co-contraction shapes active aerodynamic promptness and passive aerodynamic damping, which is the VADA effect. The shared principle is task-preserving internal motion combined with an hardening law. The analogy concerns the geometry and the incremental input-output maps. Stiffness and damping remain physically different quantities. The affine model also yields an impedance interpretation. The zero-inflow task W0 is the difference of squares term, while kd times the speed sum multiplies the air relative velocity as damping coefficient. With no external force, factoring the difference of squares gives an equilibrium velocity proportional to v1 minus v2. Thus, the differential speed component sets the equilibrium, while the common speed component sets the local damping. The visual comparison summarizes the same division of roles. In the aerodynamic module, differential rotor actuation selects the equilibrium air relative velocity and common actuation selects damping. In the variable stiffness actuator, the corresponding antagonistic tendon combinations select equilibrium position and stiffness. The correspondence is structural and local, and it clarifies why aerodynamic co-contraction behaves as an impedance shaping mechanism. A remaining practical question is whether this damping is large enough to matter. To answer it, the local force velocity slope can be estimated directly from low advance ratio propeller measurements and compared with familiar low-speed body drag damping. The standard propeller model writes thrust as air density times n squared, d to the fourth, and the thrust coefficient Ct of advance ratio j. Differentiating with respect to inflow gives the pair damping shown here. It scales linearly with rotational frequency, cubically with diameter, and with minus the low j slope of Ct. Across 62 retained strands for 16 propellers, the estimated damping ranges from 0.109 to 0.855 newton-seconds per meter, with a median of 0.296. This places the effect in a practically relevant range. The two papers can now be summarized through one map from a trim fiber to three observables. Every internal state V satisfying the same trim task at the same trim inflow has an associated power P, active promptness ρ, and passive damping sigma sub A. Along antagonistic co-contraction, all three increase. Power is a cost, while promptness and damping are useful behavioral properties. Allocation selects the balance appropriate to the current mission. The scalar aerodynamic dipole reveals the principle, but it also exposes that the next challenge is to extend task-preserving behavioral shaping to full aerial systems, richer aerodynamic interaction, experimental models, control, and design. The open geometric questions include full-range multirotor fibers and matrix-valued aerodynamic damping. The aerodynamic models should include coupled wakes, non-uniform inflow, and experimental identification. The control questions include joint power promptness damping allocation, stability, passivity, robustness, and predictive scheduling. Finally, propeller geometry and rotor layout can be co-designed to create useful fibers and favorable sensitivities. This direction defines a broader research program, and I welcome collaborations. The take-home message is that redundant actuation creates task-preserving internal states with different behaviors. In antagonistic aerial propulsion, aerodynamic co-contraction moves through those states while preserving the task. The same motion changes power consumption, active promptness, and passive aerodynamic damping. The task fiber is therefore the natural domain for analysis, allocation, and design. Thank you for listening, and please contact me if this framework connects with your work.